we get going, I just want to mention something about when the project is due. The project is due, the report is due when you do your presentations in the practice class in week 7. Now, people with the class on the Friday, I will email this out to everyone as well, people with, or the Friday people anyway, people with the Friday class in week 7, well, that's Easter Friday, so you have no class in week 7. Now, the week after is your mid-semester break, and so week 8 then isn't for 2 weeks later or a whole week later. So those with the class on Friday, you will have to hand in your report on Thursday. We cannot give you the advantage of having a whole extra 2 weeks, effectively, to do your project. So you will be handing in your project by Thursday afternoon into the subject box, and I will explain this in the brief, in Building 60. In Building 60, outside the Civil Engineering office, please be quiet. You've got all the subject boxes, so you'll drop your report in there, and then, please shush, you will have to email your PowerPoint presentation to your demonstrator by the Friday. Then when you come back in week 8, you will do your actual presentation in week 8. Okay, but you have to hand in all your material by week 7. So what that means, unfortunately, in week 8 is you miss the practice class questions that week. So I will be, rather than try and reschedule, which is just more than impossible because everyone's doing double degrees, that week I will be requesting that you come to 2 practice classes, and you have on Allocate Plus the choice of 18 other practice, well, not the Friday ones, about 15 other practice classes you can go to that week. So I will be asking in week 8 that you go to another practice class to do the practice class questions, and then you go to your Friday class to do your actual presentation. Okay, all of that, as I said, I will put in an email through Moodle to you. Once again, if anyone has any questions they wish to email me, do not do it through email, through Moodle. Email me directly to my email address. Okay, let us move on. Now, I ended last... Shh. Nudge him and tell him I'm watching him. I ended last Wednesday where I just said, oh, well, we'll quickly cover this at the beginning of this lecture, so let's give it a go. So this relates back to buckling, members under axial load. And it was, up till now, we'd been looking at symmetrical sections. So just quickly reviewing what we did last week. We said when members buckle, they have 2 axes they can buckle about. And for your project, your section is symmetrical. And for all the questions in the tute class, your sections are symmetrical. So basically, because the stiffness about both axes is the same, you don't have to worry about it. However, in real situations where you have universal beams, you have 2 axes of buckling. So what you have to realise is your section, if the effective lengths are the same, will buckle about the weaker axis. So in this question here, you're given the length and the load, and you're asked to find the most efficient universal beam that will not fail by buckling. So we're not looking at yield here. So using our formula here, we effectively will set our buckle load to equal our 500. So we'll put our pi squared EI on this side. Now I haven't written it all in there because I'm going to work, as I suggested to you, in newtons and millimetres. I'm changing my length to 3,000. We've been given, well, we haven't, but for a steel section, E is 200,000 MPa. So plugging this value in here, we then solve for our I. I'll call it the required I. So if we do, say, our buckle capacity here has to be greater than or equal to our 500. So rearranging that, you would get I required has to be greater than or equal to this huge number here. Now, based on that big number there, we would go into the section tables, which we'll have a look at here. So here are the section tables for the universal beam, and you can see your IXX and your IYY value. Now, the value we got for I required, it was greater than or equal to 2.2 to that number. Now, when you do look at the I values, take note that at the top here, it says 10 to the power of 6 millimetres to the power of 4. So it's handy to work in the units of millimetre. So we basically want to find a value greater than 2.2. So if we go down both columns, I said the smallest I has to be greater than that. So looking at the two values of I here, you will see IYY here is a lot smaller than IXX. So we look for the smallest value of IYY, that's just greater than 2.29, and that's this value here of 2.75. So this section is about 10 times stiffer about its x-axis than it is its y-axis. But you would look for the smaller of the two, and thus the section you would choose here is your 200 UB22. So the section here, if we do load it anymore, will buckle about the weaker axis, the YYY axis, YYY, the YY, the vertical axis in this case. Okay, so that semester paper, I won't do that question now because I don't think it's a terribly hard question. How about I just give you the answers for you to work out yourself and explain how to do it. Here's a typical exam question. This was the 2013 semester 1 paper. At this point in time, if you ask me could you do some extra study for this subject, I think I've mentioned already, I would go to Moodle, choose 3 or 4 past exam papers, print them off, and after finishing buckling now, you can do the first 2 questions on both exam papers. So this is generally the second question, so I'd pull the second question out from those exam papers and I'd sit down and I would attempt those questions. Answers are provided to you, so if you get them right, you can say, okay, buckling's under control. Now with this question here, it says calculate the force in member AB and AC for the system subjected to a design load of 150 kilonewton. So in order to calculate those forces, we want to know what the forces are in those members, so we would do a method of joints. So we would isolate our joint as a free body diagram, force AC, force AB, 150. And remember, our free body diagram is in equilibrium, so to calculate those 2 unknown forces, you would sum the forces in the x and y direction to 0, and you would solve for your FAC and FAB forces. So that's the first one done. Then part B, the member AB is made of grade C350. If you can't remember, that number is the number up here at the top of your design sheet. So in this exam paper, you had to actually know how to use these design tables. And what that C350 means is that the yield stress is equal to 350 MPa. So knowing the yield stress, it says select a minimum size for AB from the section table. Now member AB is in tension or compression, everyone? It's in compression. It's being squashed. So I'll leave it for you to do. You need to do a yield check and a buckling check. And when you do so, the final member size you should come up with from your tables is a 125 by 125 by 4 square hollow section. So you would come down here and find your area when you're checking for yield, and your yields and your moment of inertia when checking for buckling. So give that a go. If you have any issues, we can help you at the help desk, or you can come up before the lecture. Okay, that brings us to the end of our topic on axially loaded members. And now it's time to move on to my favourite topic. We have to have a favourite of members, beam members, members in bending. So once again, you have learnt so much. I need to tell you this so you don't go, this subject's really boring, I haven't learnt anything. Okay? You have learnt so much in this subject. You now know about loads. You can understand conversation about dead live wind loads. You know how to calculate reactions. And you know calculating reactions is the first step to calculating internal member forces. We've looked in detail at trusses, where we've used the method of joints and the method of sections to calculate the forces. And as I said, we call them the method of joints and sections to make it sound like we're teaching you something, but all the method of joints and method of sections are free body diagrams and equilibrium. You're just isolating a different free body diagram system, and you're just using your equilibrium equations. And then this week in the practice class, you will actually get a chance to practice designing members. You'll learn how to size them up based on failure by buckling or by yielding. You can yield in compression, remember, if your member is really short. So now we are going to move on away from trusses and move into beams. Beams are the most common structural form. So we are in effect going to do the same thing. We're going to learn how to analyse a beam, and then we're going to learn how to design a beam. So our structural form is beams, and our structural action is now a beam is a member that carries lateral load. So our beam now is curving. Shh. So our structural action in trusses was stretching or squashing. Our structural action now is bending, is curving. So, our member is curving, and we now no longer have tension or compression in our member. We have bending and shear. And I'll say more about that in the next few PowerPoints. So beams are the most common structural form. Here, over here, you have the simplest type of beam, just a bit of rock spanning over a lake, a river. Not a lake, just a river. So beams, all our members that carry lateral load are beams. We have what we call simply supported beams, which you've already met when you did your reactions. We can then have continuous beams that run over internal supports. We can have cantilever beams and fixed beams. So they're all beams if they're carrying lateral load, and they're all deformed and they're all curving in some way. So what we need to find out now, what we need to come up with is, where is the beam, in this case a cantilever beam, where is it being stressed the most? Because where it's being stressed the most is where it will fail. So we need to know what that maximum stress is in order to prevent failure. And this is what happens when you get failure. Okay? This roof beam here, I'm not actually sure what caused this failure to occur, but you can definitely see it has gone beyond its linear elastic loading limits. Okay. So just reviewing again, we're familiar with axial forces in trusses, but what actually is bending and what is shear? So shear is the internal action trying to slide one part of a solid over another. If you look it up, that's what shear is. But a way to remember shear is it causes distortion. Okay? I have here, let me get the document camera going here, the light on. I think it'll go on itself. What I have here is a bit of fly screen just between two fly screen edges here. And so it has a square grid in there, and I just wanted to show you what shear is. So now, if I hold one end and I apply vertical load down the other side, my load, what I'm getting is I'm getting a shearing action, not a bending action. And it's not up yet, hang on. So I just want to show you, there is my fly screen grid. So when I apply two vertical forces that are not in line with each other, that cause a couple, you will see here the deformation. Can you see it's distorting rather than curving, which it won't because it's a bit of fly screen, but you can see that distortion there. So now instead of having rectangular shapes or square shapes, I've got diamond shapes. So we get that sort of distortion in beams. Was that worth me changing it over? Yes, of course. Now we can turn that off. And here you have a multi-storey building that obviously experienced some sort of catastrophic loading through either earthquake or tsunami or something. And you can see that what was once, well in this case here, a square shape, oops, sorry, let me go to pen colour, I'll go to green. So this you can see here that distortion happening in there. It's now not a rectangular shape, it's been sheared over. So what is bending moment? We're clear shear causes distortion. Bending moment is the internal action which curves a beam. So bending moment, when a beam curves, the bottom of my ruler now, is it stretching or squashing? It's stretching, so it will be in tension. And the top of my ruler here, is it stretching or squashing? It's squashing. So the top is in compression and the bottom is in tension. One side shortens, one side stretches. So bending moments and shear forces are very important because it's from these that we get the stresses, the bending stresses and the shear strains which develop in beams. Of the two, we are, however, going to concentrate on bending moment because it's the bending stresses that we use to design. Shear stresses, if you continue to do civil, you'll look at next year. Now we're going to focus on bending stresses. Okay, so going back last week, we learnt when a member experiences axial load, bye-bye gentlemen, hardly worth coming all that way. Bye, for such a short period of time. In this hot weather. Axial stresses. Truss members, columns experience uniform. So you can see here we have a uniform stress distribution. And that uniform stress distribution will be either tensile or compressive. However, when a member bends, as shown here, we've agreed that we've got squashing the way it currently is bending at the bottom and stretching at the, squashing at the top, stretching at the bottom. So we have no longer a uniform stress distribution. So when it came to our axially loaded member, we said we have this uniform stress distribution, P on A. If we have stretching on one face and squashing at the other, our stress distribution is no longer uniform. And we define it to be linear. It's a triangular stress distribution. So now, because our section is stretching and squashing, beams are best made from materials that can transfer both tensile and compressive stresses. What do I mean by that? Stone, concrete. Not good. Thank you. Not good. Okay? So materials that can transfer both, timber, steel and reinforced concrete. The reinforcement is in there in order to transfer the tension forces. So this, if you therefore, now you understand that, or well, it's been introduced to you, now you realise, you can understand why in the olden days, with stonework as the most common building material, when I say common, they would just go to a stone pit and pull out all the stonework. It was easily sourced. Stone, however, we know crack under tensile stresses. So did they build their structures as beams? No, they built them as arches. Big doorways, aqueducts here spanning rivers, big churches, cathedrals. The roof structure is an arch shape. Why is it an arch shape? Because the principal structural action in arches is compression. Vertical loads, shown here in red, are turned into compression radial forces, shown here in blue. And thus using stonework worked for them. So They used stonework. It was easily sourced. Once they discovered iron and steel, they realised they had a material that could transfer tensile forces, and that's how buildings developed. Now, the Romans were very smart, okay? They loved arches and domes. And as I said, they're a particularly good structural form to build in stone as they primarily experience compression forces. The Pantheon, has anyone been there in Rome? This building here? Yep, it's a cool structure, isn't it? There's a hole at the very top, and when the sunny and the light shines in, it's really cool. It was built 125 AD. It still holds the record as the largest unreinforced concrete dome at 43.5 metres. Not such a record really, because you wouldn't build without reinforcement nowadays, but it still holds the record. The dome thickness varies from 1.2 metres at the top, 4.6 metres up the sides. They built to last in those days. So the Romans actually were the ones that actually invented concrete, because it was a low-cost alternative to bringing in the masonry and the stonework. So the Romans were smart. The Greeks were smart as well. But how did the Greeks build? Have you ever seen a Greek arch? You must have done some history and some art and some travel. Greeks didn't build with arches. They used beams and columns. You can see here this beam, it's a lintel beam and columns. And we know stone isn't good in bending, so see how these columns are always close together? That wasn't necessarily because they liked the look of it, it was because they were forced to keep the columns a certain width apart, because beams experience bending, tensile forces, and this tension was a problem. It led to cracking. So if you do get a chance to see the Parthenon as distinct from the Pantheon, okay, have a look, and a lot of these lintel beams up here are cracked. So the maximum span of their stone beams was approximately 2.5 metres. I say the maximum span because that size lintel beam was about the biggest they could actually lift up with ease. So of course you can always build them bigger and they could span further. But in terms of a common lintel size, 2.5 metres was their maximum span. And they used timber sparingly. This structure would have been covered in timber, of course, but they didn't have many trees in Greece because they'd cut a lot of them down already. Okay, so they used timber, which was very scarce, to span greater distances. Otherwise, that's why the Greek structures have a lot of columns. It looks good, but the Romans found a way around it by building arches. So just a bit of history there. So let's go back. We now need to calculate our shear forces and our bending moments. So, how do we do it? Am I going to teach you a wonderful new method? Yes? No? I'm going to teach you how to apply equilibrium and free body diagrams yet a different way. Is it actually different? No, it's not actually different. It's actually exactly the same. So you could walk out now, and if you really understand equilibrium and free body diagrams, you could do this on your own. But since I'm here and you're here, we may as well go through it. So, we have agreed, going back to trusses, that the structural action in our trusses was axial tensional compression. So when we did draw our free body diagram and cut through our members, we only had, guys, stop chatting, or chat quieter if you're going to chat, okay? Our structural action, when we cut through, we only had one unknown at each member. Now, even before we did trusses, when we looked at internal pins, which you did in the quiz last week, when you cut at an internal pin, you know you have a potential horizontal and vertical force. When you, however, cut a beam, you have three potential unknowns: a moment, an axial force, H shown here, and a shear force, V. So, three unknowns at the one cut. So for a beam, the internal forces in general are axial, shear and bending. So here I have my free body up the top, and down here I create my free body diagram by cutting my closed loop boundary, having it cut through the member, and thus in my free body diagram I have three unknowns at the cut. So thus when you're dealing with beams, you make one cut. And at that one cut, you have your three unknowns. When we were dealing with trusses, and we used the method of sections, we could cut through a section like so, and we would expose three unknowns, but they were all axial loads in the members, in three different members. Shh. I said sound travels really well in this room. It travels down really well and up really well, so I can hear you. So if you're going to talk, just quite, well, why don't you just wait 25 minutes and talk later? Okay, so we have three unknowns at a cut. How do we solve for those three unknowns? Nothing new, we're going to use equilibrium. But before we do that, we need to confirm our sign convention. And this is where people get slightly confused. Now, when we use equilibrium, we use our Cartesian positive sign convention. Up is positive, to the left is positive, anti-clockwise is positive. However, if my beam is bending like so, assume I've got my chin still on it, I'm just holding it down here. A positive bending causes a beam to be happy. Smile, positive. So if you said, what's the bending moment in this beam? Just by looking at it, you know it's a positive bending moment. So anything that causes hogging, we call this hogging, is sad, is negative. So think of sad shape, negative, happy face, positive. So that's the sign convention for what the internal moment is. Is it a positive moment? Is it a negative moment? If it looks like that, it's positive because it's happy. If it looks like that, it's sad because it's sad because it looks sad. Yeah? So I have a cantilever here. This is the wall. I'm grabbing it. I'm applying a point load. Is the bending moment in my cantilever beam positive or negative? Because it's sad. Okay? As simple as that. Yeah? If I have a support here, could you come and be a load for me? Let's just run through all of this. Okay, you be a load at the end. Positive or negative moment? Okay, can you apply a load here as well as the one at the end? Okay, what have I got here? I've got a positive moment here. I've got a negative moment at my support. Okay? So where it's happy, it's positive. Where it's sad, thank you very much. Okay, yeah. So when you look at equilibrium, anti-clockwise is still positive. That doesn't change. We still say anything anti-clockwise is positive, but that's distinct from what an internal bending moment actually is. Now when it comes to shear force, anything, when you show your two free body diagrams, anything that causes anti-clockwise rotation. So as drawn here, I have my shear force up on one side and down on the other. And can you see here that causes an anti-clockwise rotation? That would be considered a positive shear force. Now, in saying all of that, oh my God, there's all these positives and negatives I have to get used to. No. If you just follow this method, it will all work out for you. So when you make a cut, and you consider the free body diagram to the left of your cut, if you draw your moment anti-clockwise, your shear force down and your axial force out, you will get the right positive and negative values. Because have a look there. See that moment is drawn, causes a positive moment on the left of the cut side. If I now go right of the cut, can you see my moment now? It's clockwise, but it's still causing a positive moment. So if I was looking right of the cut here, when I come and take moments at the cut here, and they equal 0, I would say I have minus m in my equilibrium equation because it's going clockwise. However, when I would work on the left-hand side here, and I would take moments at the cut here, because my moment is now anti-clockwise, I would call that plus m. We'll do an example with numbers anyway. Just don't confuse the two. Okay, so how do we calculate these internal forces? We have our three unknowns, bending, axial, shear. It's obvious how we calculate them, I think. To find axial forces, all the forces in the x direction equal 0, we solve for h. In the y direction, sorry, oh yeah, okay. the axial force. When you look at your system, if you have no axial force applied, you can assume everything's zero. All your reactions will be zero, so there won't be an axial force in the system. So take note now, I want to trick you in the exam, on the test. I just put a little a horizontal force in there because you forget about it. Okay? But it's not difficult anyway. To find shear force, we sum all the forces in the y direction. We equate them to zero and we solve for V. And following on the bending moment, we take moments. For bending, just like when we did the method of sections, there's a best place to take moments. With method of sections, it was where two of your unknowns met. Here, take moments at the cut. That's usually the easiest place to take moments. Again, I'll do problems. Okay, and here's our first problem. So determine the internal forces, shear, axial and bending 6 metres to the right of point A. Before we do that, what do we have to do? We have to calculate our reactions. So by calculating my reactions here, I am considered free body diagrams, but my free body diagram is in effect of the entire system. So looking at reactions here, all the forces in the x direction equal 0. Because I had my triangle at A, that represented a pin support. A pin support is me grabbing my ruler with my two fingers. I can't pull it sideways and I can't force it up there. So there's an unknown horizontal and vertical. So I have an AX value. This time I have a 10 as well applied to the right. So therefore my AX is equal to minus 10 kilonewtons. It opposes it. I will take moments next. Where shall we take moments? I usually take it at the left support. Let's take moments at A. So taking moments at A, remember AY causes no moment, AX causes no moment. I have my 30 kilonewtons. My perpendicular distance is 4. Clockwise or anti-clockwise? Clockwise, so it's negative. This UDL load here, I have an equivalent point load here of 20 times 4 metres, which is 80 kilonewtons. So my force here is 80. And when we apply this equivalent, we apply it in the middle of the actual uniformly distributed load. So that's 6 metres away. So I multiply that by 6. That's also causing clockwise, so that's minus. Does this 10 kilonewton here at B cause a moment? No, because you can trace that arrow back to A, so it has no perpendicular distance. So our final force is By. It's 8 metres away. As drawn, it's going anti-clockwise. So from here, we can solve for By, and that's equal to 75 kilonewtons. And now all the forces in the y direction equal 0. AY minus 30 minus 80 plus BY equals 0. So AY is equal to 35 kilonewtons. So you're all sitting there going, yeah, we've done this before, I get it. We're going to do exactly the same thing to calculate internal member forces. So the question is asking us to determine the internal forces 6 metres to the right of point A. So I'll come over here. We calculated that to be 35, 10, and 75. So where our free body diagram has to pass through. So 6 metres. So in drawing our free body diagram, we're going to cut through where we want to know the moment. So we can either deal with that free body diagram to the left or a free body diagram to the right. I'll do it both ways, show you we get the same answer, so you can go, okay, that all looks good. And then it's up to you which free body diagram you want to deal with. So, just as with the method of joints, I'm always saying draw your joint, draw your free body diagram. Actually, I might spread them apart a little bit just to give ourselves room to draw those internal forces. So I'm just splitting them a bit. So I said at the cut, draw your moments at the cut so they make a happy face. See that moment there will cause a happy smiley face, and that moment on the other side will cause a happy smiley face. I've got 75, I have 10, I'm cutting it at 2 metres, so that's 20 kilonewtons per metre. Now axial forces always have to be tension, and the shear forces, we said, as a couple, create anti-clockwise rotation. So it would be up on that side and down on that side. So we have V, H and M. And can you see I've drawn them equal and opposite? So when effectively we join it all up, it's all in equilibrium. So finishing our free body diagram here, 35, 10, I've got 30 kilonewtons here. That's 4 metres, 2 metres, and we all know the value of that UDL load, so I'll just draw it in. So I have 2 free body diagrams, and both are in equilibrium. So let's actually calculate those 3 forces both ways and prove to ourselves that's the case. I'm going to go blue. Okay, so let's work with free body diagram 1. So, anything new? No. Equilibrium, all the forces in the x direction equal 0. On my free body diagram I have my 10 applied, plus h equals 0. So, my horizontal force is plus 10. What does that plus mean? It means it's in tension. If I now go to free body diagram 2, all the forces in the x direction equal 0. I have my 10 applied this time, minus h equals 0, and lo and behold, h is 10 kilonewton. Yes, I've drawn it to the left in one and to the right in the other, but drawing it away like that indicates tension, and they're both positive, so they're in tension. So if that structure, say, was a beam and it was a big rusty beam and it had rusted through there, and I said, I'm going to cut it in half, could you please hold both halves while I cut it in half and then stick it back together? You would be, it's in tension, so you would be pulling inwards with both hands to hold it together. That's what the beam's doing. Okay, let's now look at forces in the y direction. All the forces in the y direction equal 0. I have my 35 up here, my reaction. I have my 30 point load down. And then I have minus 20 kilonewtons per metre acting over 2 metres. And then I didn't call it up as V there, minus V, because the V I've drawn on this free body diagram is down. All of that equals 0. And from that, V is equal to minus 35. What does the minus mean? I've drawn it down, it's going up. So, when I do the same on the other side, I've got fewer vertical forces to consider. My V is up this time as drawn. Then I have minus my UDL load down plus my reaction up equals 0. And lo and behold, V works out to be 35 kilonewtons, which means on that side, instead of up, it's down. So again, if I asked you to hold that beam, just got to get it right, you would be pulling down on this side and pushing up on that side. So as well as pulling up and pushing down, you're also pulling inwards. So you're being big and strong here. But if all you did was pull up and push in, you would just be an internal pin. It's now curving there, so as well as doing that, you now have to bend it as well. So, those two people usually can work out. It's the bending again that seems to cause a problem. Let's take moments, and I always take moments at the cut. Taking moments at the cut, V isn't in your equation. If you've made an error in V, it doesn't matter. So taking moments at the cut here, we have at the cut M. That's the internal moment we're trying to calculate, M. So M, as drawn, is anti-clockwise, so it's positive. Then I have my reaction 35. That's acting 6 metres away. At the cut there, that force is applied is causing clockwise rotation. So put your finger at the cut and go, okay, I can see it's causing clockwise rotation, just like you did for reactions. So that will be minus. Then I have my 30 kilonewton point load, and that's times 2 metres, plus or minus? Plus, cool. And then we have plus our 20 kilonewtons per metre times 2 metres is my total load, times a lever arm of 1 metre away. Can you see if I put an equivalent, I'll just draw it in another colour here just so you can easily see it. If I draw my equivalent point load here, can you see it's acting there? We put it in the middle, so that's 1 metre away from the cut. Which blue did I use? All of that equals 0, and by doing that we get a moment of 110 kilonewton metre. It's a positive moment. Do we expect it to be a positive moment? Yeah, because we've got a point load down and a UDL load down, and our beam is curving like so, and it's happy. So yes, we expect our moment to be positive. If you had got a negative value out of there, okay, then based on that sign convention you'd be wrong. It's possible if you drew your moment round the other way, a negative is just telling you then that it's opposite to the way you drew it. So just memorise which way to draw it. So let's just finish this one off. We're taking moments at the cut this time. Our moment as drawn here, it's clockwise, so it's minus M. Then we have plus 75 times 2 metres. And then we have minus 20 times 2 times 1 equals 0. And from all of that, our moment is 110, which is what we'd expect it to be. There is nothing more to calculating internal forces than that. Okay? So why do you still get it wrong in second year? I have no idea. Of course, things can look a bit more horrible. This would be what I call the scare question on the exam. Let's scare them. But if you remain calm and say, I know, I just have to apply equilibrium and free body diagrams, you're okay. So let's have a look at this system here. Now this system is drawn, if it had, there's an internal pin there, there's a pin support here, there's a pin support here. If it had a point load applied up here at the joint, this would be a triangulated structure and all the internal forces would just be axial. However, because the forces now are not applied at the joint, because that was the assumptions of our truss method here, can you see here my member is bending? And with a load here, this member is bending. So as soon as you can see some bending, some curving happening, you know it's a beam. Up here, can you imagine there's any curving in here if the point load's applied at the middle? No. So this, to calculate these two forces, you would use the method of joints. Okay, we want to know those forces. I'm not going to calculate those those reactions again. This is the problem we did back with internal pins. So let's say we know what our reactions are. The question is then asking you, what are the internal forces here 2 metres up? So if you want to know the internal forces there, you know that is where your free body diagram has to cut. Yeah? Now, it's at an angle. Are we going to freak out? No. So, coming over here, there's my free body diagram. So I'm going to draw everything in my closed loop boundary. And as I said, The reactions we calculated a couple of weeks ago was a 30 to the left horizontally and a vertically down 6.66. Now at the cut we have, it's a beam, an axial, a shear, a bending. So we now need to draw these as an axial, a shear and a bending. They are at an angle now, but the axial has to be an axial force, the shear perpendicular to the beam, and our bending. So this is our system, and again you were given enough information to work out that angle. So I'll call this now H, V and M. I could take that whole, I won't rub it all out, I could take the beam away and just say I have 5 forces here. Well, 4 of them are forces and 1's a moment. So I could just up here go, okay, what I've got is I've got this system of forces here. Doesn't matter what the structure looks like, forget about the structure. That system of forces is in equilibrium. Tell me what those 3 unknowns are. Because you have 3 equations, you can solve for your 3 unknowns. So let's start off taking moments. So admittedly, we have a slight complication here in terms of what's the horizontal and what's the vertical distance. But you can work that out because you're smart. So that distance in there would be 2 cos 53, and that would be 2 sine 53. So now, when I come and take moments at the cut, remember a moment is a force times its perpendicular distance. So I have M first of all. Now my 6.6 vertical force there is a vertical force. So what's the perpendicular distance? It's the 2 cos 53.13. Remember I said when we were doing reactions, vertical force, horizontal distance, horizontal force, vertical distance. Now, as drawn, clockwise or anti-clockwise? Anti-clockwise, so that's plus. And now I have the 30 to consider. My force is 30. The perpendicular distance, it's a funny 3, is 2 sine 53, plus or minus. Stick your finger at the cut, trace it round, it causes clockwise, so it's minus. So from all of that, the moment in that member is 40 kilonewton metres. So we know one of our 3 unknowns. Now, for forces in the y and the x direction, we're not going to deal with the horizontal. We actually want to know what this h force is. So we are going to just rotate our axes round. That's the easiest thing to do. The x-x axis lines up with h. Sorry, the x-dash axis lines up with h, and the y-dash is perpendicular. So now, taking moments, not taking moments, I'm going to say all the forces in the y-dash direction equal 0. Now, this is just a bit of trig. You are going to resolve these reactions here into that x-dash y-dash axis. So that angle is 53, so you've got to be good at trig. I'll just write 53 here instead of 53.13. Now which angle in here is 53, the top one or the bottom one? Bottom one, I heard one person say. I'm going to assume you are all thinking the same thing. Okay? So in the y-dash direction, what have I got? That's my v direction. So I have minus v because it's going down. Now when I come and look at my 30, that has a component in the y-dash direction. That's the sine component, and it's going up, so it's positive. When I look at my 6.6, it's this force here. Can you see where I'm waving my little marker? So that's going downwards, so it's minus 6.66. Is it sine or cos this time? Good. cos 53, all of that equals 0. So from that we can calculate our shear force. It's nothing hard here. Okay, you finish this one off and you make sure you get a horizontal force of 23.32 kilonewtons before next Wednesday. See you next Wednesday. Sorry? This Wednesday, not next Wednesday. See you in 2 days.